Hi all. Uh, I don't think anyone has joined, so I'll just wait. I'll be on mute. Hi, thanks. Hi, Rohi. I hope you both can hear me, right? So then I'll start sharing my screen. Okay. Let's wait for 1 minute or maybe sometime and then we can give it a start. Or maybe we can start because let's not waste time, right? So I will just continue from where we left off yesterday. I'll just quickly clarify what the confusion was. So thanks to Rohi for correcting that. We do have the skewness, which is either this or either this, right? So the skewness is actually this tail thing. So this tail over here is on the right hand side. This is the right side. This is the left side. So this is why this is a right skewed. Okay, this is RSD. So a right skewed distribution, and this is LSD, not to be taken in a different way. This is left skewed kind of a distribution. So here I have the left side here and right side here. Okay, so what I was saying yesterday related to this is that, let's say in this kind of a distribution, this y-axis has no value because this is just the frequency. So we are going to look into frequency today before we proceed. So and then we have to quickly look into range and interquartile range. I believe I have already covered these two yesterday. So we can directly go on to variance and standard deviation, and we will look into the frequency distributions as well, because we need to understand what this graph means. So if this is the x-axis where I have the variate, so this is yet another name, right? You can try to remember this. Variate is just another name of the variable for which you're trying to take the diagram. Okay, so this diagram is also known as cumulative frequency diagram, or I should not say cumulative. I'll remove that word because cumulative is going to mean something entirely different at later stage. So I'll just say frequency diagram, FD. Okay, so these are the frequency diagrams in two different cases that we have found for two different variates. The variate is my x-axis. Okay, now what I was saying yesterday is as simple as this middle line is always going to be the mean. Okay, so this mean is going to remain the same. What I mean by that is, If I want to find the mean, and I'm going to define mean as m, okay, so I'm going to say mean as m, mode as mo, and median as me, okay, just to signify which is mean, median, and mode, because all of them start with m. So if you look at this point over here, this point on the axis is going to define the mean, and not this point, okay. So it is not the point on the graph which is meaning the mean. The mean is here, okay, this is the mean value. The mean or the average is always on the axis, okay. Now if I'm trying to calculate the mode, in this case the mode will be the number where I have highest frequency. The highest frequency is at the top, so mode value is here. So if I represent it like this, okay, this is going to be where the mode is, okay. And then if I carefully look into uh, the, the the aspects, then I will be coming to know where the median lies, and in that way I should be able to find out which is greater than what. So I have this, which is my mode, right? So in this case, this value over here is mode. Why is this? Because all of the accumulation has happened because of the slant line. The slant lines are actually adding on to this top value, okay. I hope that there is no confusion in here up front, and I hope you can see my screen, right?
Yes.
Okay. Okay, so that's the first of all, that is the overall thing. And then what I would like to look into first of all is the definition of that variance and standard deviation that we were looking into. So let me just clear all the drawings and give me 1 minute. Okay, so yeah, so what I'm going to do, I can write, but let me just it will be better if I use Excel. Hold on, because it is easier to explain uh, the formulations of variance and standard deviation using Excel. So let me save this notebook and open Excel. Okay, okay, I have opened Excel. Let me increase the zoom and share the Excel. So I'll new share and Excel. Are you able to see my Excel?
Yes.
Okay. So let's say I have some numbers, and I'm going to take some numbers, which is, let's say, the age of a certain set of people. So I have 11-year-old, 12-year-old, 13-year-old, 15-year-old, then again a 12-year-old, then again a 17-year-old, then again 14. So I'm just going to type some, let's say, random numbers. There will be people on the higher side as well, and so on. So I have a variable here which is having the age of a certain set of, let's say, people. Okay, I don't know who those people are, but this is just a hypothetical example. How do I calculate the average? Average is something that I have looked into, which is the arithmetic mean. There are two more types of mean. We have not looked into them. We may not really look into them because they do not really help you find out anything. Okay, there are two more types of mean. I'll just quickly tell you what those means are. Those means are known as geometric mean and harmonic mean. Okay, the geometric mean and harmonic mean really does not add any value when it comes to looking into an average, because when we are looking into relative metrics like this, the advantages of mean that we have already seen is that it is clearly defined. There is no complexity in the mathematics. It can be easily calculated. It gives weight to all the items. Okay, so if there are outliers, it will be dragged on one side, which is a good thing actually, because then we'll come to know whether there is an outlier or not. But then the disadvantage is it may not really always physically represent the right numbers. Example given, if if I take an average of these many ages, I get an average which is 16.2. Okay, so I get an average which is 16.2. I hope you know or you have Excel. If you don't have, I would strongly recommend try to get hold of Excel from some place. Okay, because this is a very, very important tool. And if you have seen the curricula that we created, Excel is also part of that, because Excel is really useful when it comes to data analysis. Please don't be under this impression that we are in the age of big data and that's why all these fancy tools are going to come handy. That's not the case. Okay, so Excel is the first place where I would go. I do almost all of my exploratory data analysis in Excel. Now the point here is what I wanted to make. Average in this case is 16.2. Now that 0.2 in age does not really signify anything to me. Okay, that 0.2 does not mean anything. point2 means what? Am I going to represent that as the number of months after I am 16-year-old? Maybe, may not be. It should ideally have been represented as 16 or let's say 17, but 16.2 is not really a very good way to represent age as far as the physical nature of age goes, right? But then average is also affected by the undue high and low values, which is also known as the outliers. But I have calculated the average. How did I calculate the average? Is as simple as I do a function which is known as sum. I take the sum of everything, and then I have to divide this by the number. So how do I divide? On the left hand side, you can see the row numbers, right? So it starts from 2, ends at 16. So there are 15 entries. I simply divide it by 15. So I get the average, which is 16.2. So this is the average age of this data set that I have. Now to find the variance is what? Variance is how much is the data varying from one place to another, as we have seen yesterday, with or without the scale. The scale in case of variance as well as the case of the standard deviation of the data is not going to matter, right? But what we are going to say essentially is that, let's say again, going back to yesterday's example, if I have this 5 data points and 3 is the mean, then and the difference from each and every point towards mean is on an average 1 or 1 on average 2, I might say that the deviation of data is equal to 1, although I'm not sure whether it is really equal to 1 or not. I have to prove that. I have to mathematically find that out. But the essence of variance is that I try to understand what is the difference or the distance between all other points in the data set as opposed to the mean. So how close or how far the points are there in my distribution as opposed to the average point. So if I have 5 points, these are not groups, by the way. Please don't get confused with the groups example which we took earlier. The age groups, that was a grouped example. Okay, this is not a group. I just have 5 numbers, 1, 2, 3, 4, 5. These are the 5 elements which are there in my set. And then I'm trying to calculate the mean. Obviously, the mean is going to be 3. Right? If I simply select all the numbers, there's a very easy trick in Excel. Select all the numbers. At the bottom, you can see the average of the selected cells, the number of selected cells, and the sum. Okay, the sum is equal to 15, count is 5, hence the average is equal to 3. Okay, so you take a total, it becomes 15. There are 5 elements here, hence the mean is this. Right? So if I take this as the mean, then how much is the difference between each and every value, or how much is the distance between each and every value from the mean, is what we are going to calculate as part of variance as well as in case of the standard deviation. Okay, so that is exactly what we are doing. But the only difference between standard deviation and variance is that standard deviation is the standard way or the mathematically correct way to represent the variation. And we will come to know about it when we look into the formula. Okay, so how we calculate that is that, first of all, we take the data set and we have calculated the average, right? So these are my points. Okay, from each and every point, I take the point or I take the data point and I subtract the mean. Okay, so what I do is equal to this cell or whatever is the value in this cell minus the average value. Okay, to properly do this, I will have to use the dollar formula. I will tell you what these dollar things mean at a later stage, but I can simply drag this function now. And I can clearly see if I go down, right, the function, you can see the function over here. It's A2 minus K1. Okay, K is this cell, 1 is this row. So K1 is this. So A2 is 11. A2 minus the average is this. Okay, A3 minus the average is this. You see dollar, using the dollar sign, it doesn't change. If I don't use the dollar sign, it's simply going to drag the values like this. So I have calculated something which is each point minus the mean. So I have simply subtracted the mean from each and every point. So what happens if I take a sum of this? I take this and there is an auto sum function over here on top. If I take a sum, it is something like this. Okay, it is almost always not going to add up. Okay, because this value is not going to mean anything. Usually, if you have a very good normally distributed kind of a data set, if you divide the mean, then it is going to be a problem because you will have equal number of negative as well as the positive value. So I have simply divided each and every value from the mean, and then what I'm doing is I'm trying to get rid of this plus and minus sign. So without sign, okay, I don't want any sign because that minus sign is not meaning anything for me, right? Minus of age is nothing, right? I cannot have a minus age. So I need to do something about it. So what I do, I simply take a square of this. So I take a square of this. Okay, if I do a square of this, I get this number, right? So this is how I have calculated the variance. Okay, no, this is how I have actually calculated the square of the value. Why have I done that? Is because I don't want to represent the age in a way which is not part of that scale. So that scale is going to be violated if I don't do a square, right? So once I have done the square, now the values are all into positive, and because the values are into positive, then it becomes quite easy for me to look into the essence of these. So what I'm going to do now, this square value that I have got, if I take a sum of the square, okay, so if I take a sum of the square, I take a sum of the square, it becomes 224. Okay, so the variance, sorry, variance, give me 1 minute. I'm actually getting a small call. Huh? Give me 1 minute, I'll be on mute. Yeah, okay. So now the variance, how the variance is going to be calculated. I have taken the difference from mean, then I have squared it so that I can get rid of the sign. Now what I'm going to do, I have taken the sum. So the sum comes to be 224. Okay, the variance is simply equal to the sum, okay, divided by the number of elements which I have over here. So how many elements do I have? From 2 until 16, it means I have 15 elements. So if I simply do a division, so this is the variance. Now there is a problem. This number really does not signify the variation in the data. Why it does not do that is because to correct this plus minus thing over here, I have done a square value. And then also there is one more problem in this formula. I'm going to tell you what is the problem. Okay. So because we have done a square, I have lost the scale. So I have to get back to the original scale in which the age forms. And that is where I calculate the sorry, I'm not going to write it over here, or maybe I can write it over here. So I'm going to write standard deviation. Okay, standard deviation is in the same scale. It is just a representative number. It does not mean the actual age. Okay, so don't get confused that standard deviation, whatsoever is going to be the value here is going to be a value of age. It is not. It is not a value of age. It is simply a representation of how much numerical deviation is there between each and every points in the set. So how do I find this out? I have done a square, right? So to correct that square, I have to do something. Okay, what do? I simply take a square root of this and I get the standard deviation. Right? So if I take the average is what? 16.2. On an average, if you see each and every point in this set, okay, is approximately 3.86 value away from 16.2. Right? It will not be exactly the same. Don't try to make it exact same. So let's say I'm going to take this age column over here again, and then I'm going to age plus SD. So SD is the standard deviation here, right? So what I can say is I'm going to add this with this, okay? But I'm not going to do F3. I'm going to do $F $3 so that it doesn't change the value. Okay, so if I do a sum, it is almost same. It is not really close to the mean. So plus minus is going to be applied here. So I can do another thing over here, which is like age minus s dot d. Okay, and here what I'm going to do, it is 11 minus the standard deviation. Okay, and then I'm also going to use a dollar sign over here, and then I'm going to say this, right? So a plus minus of standard deviation is where that value is going to fall. Right? So this value falls between the average. Oh no, sorry. I have done a mistake here. This should be M1, $M, $1. Okay, so plus is this and minus is this, $M, $1. Okay, so all the values of this kind of range data is going to fall between this range. So the mean of the age, I can actually delete this part. This is not really required. And I can add just a column over here. So the mean of age. So this is not age. Huh? Mean of age plus the standard deviation becomes 21 something, and mean of age minus the standard deviation becomes something like 12.33. Approximately, this is the range in which my data falls, and this is how the data is dispersed amongst the mean or the average of the data. So that is the essence of the standard deviation. So what that clearly means is that essentially, if you look at a data set, try to find out the standard deviation. And there is a very easy way of doing that as well. There is a standard deviation formula. Okay, if you are doing that in Excel, you don't have to do all these things. Just to explain you, I've done that. There is already a formula. Put that formula in place, you will come to know what is the standard deviation. By looking at the standard deviation, what you can say, let's say I have a data set with a standard deviation 3.86. I can clearly say that the minimum and the maximum value is not really too far away from each other. But if I have a data set where the standard deviation is 386, rather than being 3.86, the standard deviation is 386. In that case, I can clearly tell you there is some problem with the data, because there is a huge range of numbers which is there in the data. That is the essence. Why we don't look into variance is because variance was not in that scale in which I needed that data or I had that data. Why? Because I squared it here. Right? So this is what the thing is. Let me just see if I have done things correctly. N1 is, yeah, yes, good. So this is what variance and the standard deviation is. We will quickly move on to the distribution part. In the meanwhile, if anyone has any questions, please let me know. Any questions from you, Rohit? Saransh?
Make this standard deviation 3.86. So this means one standard deviation away, right, from the mean.
Yes, I did not want to pick that point right now because we don't know what is the exact usage of standard deviation. But good that you have actually brought it there. So just to quickly say one more use case. So you can say this is one of the use cases of standard deviation. If you have a mean, and mean in this case is 16.2. So I'll just write it over it, 16.2. Okay, so this plus SD, okay, can also be represented as plus 1 into SD. Okay, so if I do a 1 into SD, that is also the same thing, right? Because I'm simply multiplying 1 with this. So this is one range of value. Okay, so if I take this, oh no, sorry, I should have not taken this. I should have cut this and put it over here. This is the maximum, this is the minimum. Oh no, sorry. Copy and paste. I did a cut paste. So this is like the mean. Okay, and I can call this range as one standard deviation. Okay, or one SD. Why is this known as one SD? Is because from the mean I have added one SD here. From the mean I have subtracted one SD here. So this is the range where I am actually falling into. Is that the right thing I've done? Yes. So minus and plus. So this is the range in which I am falling. So this is one SD. Okay, or one standard deviation range. Okay, I can do a similar thing with two standard deviations. I can do a similar thing with three standard deviations and so on. And there will come a time when once I do that, I'm going to arrive at a very important kind of a formula, which is otherwise known as the central limit theorem, or it is also known as the empirical formula, which becomes the basis of the central limit theorem. So when we look into central limit theorem, we are going to look into that. So ideally, what we are also going to do is two standard deviations over here and three standard deviations over here. Okay. We may want to quickly look into that maybe in the next class. So tomorrow we may want to look into that, because 3 standard deviation, because I just have to explain you what is the distribution and then we can go ahead. I think if there are no other questions, we can proceed. Okay.
Yes.
Okay. So the next thing which I wanted to show you, I'll save this Excel and share it with you later on. So maybe I'll just go back to that Notepad. I hope you can see it here, right? So no, let me go back to that Excel. It will be easier. It will be easier in an Excel. So this is variance and standard deviation that we have looked into. Let me create another tab. And this is where we are going to look into something which is known as the tabulation, or how to perceive or conceive, let's say, distributions in the data. So how do we do that? Let's say I have some table, I have some value, I have some random values of the rent which is applicable on 40 houses. Okay, so I have 40 houses in my area and I have some rent which is associated with it. So the rents are like 5, 6, 7, 8, 11, and so on. Okay, now you might be wondering, how is this the rent? So when I'm taking the data, in case of, let's say, statistics, there are already a set of assumptions which work along with each and every data. Okay, in this case, the assumption that works is that I have a scale of that data. I have to be explicit about the scale of the data. I can't simply tell you that this is the rent of a house. I have to also tell you that I have scaled it to thousands of rupees. So ideally, the rent will be 5 into 1000. And this is into the rupees format. So the 5,000 rupees. So 5,000 rupees is the actual rent. I am simply representing 5,000 as 5. So if I have rent 5,000, I simply divide that by 1,000. I get a number. So if I have numbers like this, 11, and then let's say I have, I don't know, 15. I have, let's say, 20. I have, let's say, 8. I have, let's say, 11. I have, let's say, 25, and so on. Okay. I made a typo. Okay, so there are more numbers like this. Only at looking at these numbers, I can try to find out mean, median, mode, and then the standard deviation and the variance that we have already looked into. Okay, then there is one point I believe I have missed into the variation. So let me go back. Okay, why I would like to go back is because, let's say, this is the age of few people, right? How many people are there? Okay, 15 people are there. Now on this earth, do we have only 15 people? The answer is no. We don't have only 15 people. So if I have taken 15 people from the entire, let's say, population, so this becomes my sample, right? Because the population of the earth is into crores and crores, right? It is into billions. I've only taken the age of 15 people over here. So this is obviously a sample. I can't take the entire population here, right? Because it is a sample, there is one thing that we need to change, and that is a formula of variance. We actually have to divide this by 14. Okay, we actually have to divide this by 14 and not by 15. We have done an n minus 1. So n in this case is equal to 15. The count is equal to 15. You can see over here. But we have to divide the sum of squares by 14. And this concept is known as, otherwise known as Bessel's correction. Okay, there is a person, there was a statistician named Bessel who found this out, that it depends on what kind of sampling technique you have used, my friend, that you have come to this 15 samples. I don't know what kind of sampling techniques you may have used. I have simply got the sample. I can't assume anything about it. Because I have got the sample and I cannot assume anything about it, there is no point for me to blindly apply all the out of the box formulas which I have. And that is exactly what is the essence of Bessel's correction. What Bessel's correction usually says is that I am going to use n minus 1. Okay, n minus 1 in place of n, so that I can make the corrections in the sample statistics to underestimate the actual parameter. Now this statement is a very confusing statement. So in plain and simple English words, what it means is, there are few parameters I have used to prepare that sample out of the population, right? There are some assumptions, some kind of sampling that I have done. After that only I have come to that kind of a sample. I have taken 15 by doing something, right? Now, this calculation always has some kind of a bias, because there will always be sampling bias. Sampling bias is something that even if you use best of the techniques, you will always have some kind of problems with the sample. Okay. Okay. One thing I wanted to quickly tell you is that we are only three people here, right? So because we are only three people here, I don't think that 40-minute time limit will be applicable. So maybe we can extend up to 9:30 if that is okay with both of you.
Yes.
Okay. Yeah. Okay. So what I was saying is there can be sampling errors, and because of that sampling error, there will be errors introduced in the calculation of the sample of the variance as well as the standard deviation. So that's why we are no longer going to call that a variance, and we are going to call that a sample variance. Variance is where I'm going to use n. So in the division, I'm going to use the number, which is the population. The sample is always a subset of the population. Okay, and how usually mathematically it is going to be represented, you can find this in many books, is something like this. So it is part of the population. S here represents the sample, P here represents the population. So S is just a sample or a subset of the population. Okay, population is a very big set. So when I'm calculating the variance for the population, I'm going to divide my sum of squares by n. N is the number of items which are there in the population. But to correct the bias or to handle the error which is there in the in the correction which is introduced in the calculation of variance and standard deviation, because of the way I have added any bias or any errors into, no, I was wrong. There is also a 40-minute limit, so we have only 10 minutes left. Okay, so S is the sample here. There can be errors while collecting it, so that's why in case of n, I'm going to do n minus 1. Okay, so that's exactly what I've done over here. If you're doing it for a sample of data, if let's say you have a lot of data and you're doing it for a sample of data, always do n minus 1. Okay, but when you are using the standard libraries into Excel or any other programs, it's not going to do that out of box. You have to figure out ways to do it. Okay, so if you are going to use, let's say, standard deviation function which is there in SciPy library, the SciPy library, when we look into that, when we do hands-on, we'll come to know SciPy library does not really know whether you are calculating a sample variance or a population variance, because you have to tell it or you have to manually calculate. Okay, but let's look into the distribution thing. So we were looking into this house rent kind of a problem. So I have rent of many houses which are there. So let's say I have, let's say, I don't know, my total number n, the number of samples I have is equal to 40. I have specifically mentioned the number of samples. Okay, number of samples is equal to 40. One good way to represent this data is also known as a frequency table. So how we represent this data as a frequency table is something like this. Let's say I write the rent and then I write the frequency. Okay, so let's say houses with 5,000 rent, the count of houses where rent is 5,000 is 1. The count of houses where rent is 6,000 is 2. The count of houses where rent is 8,000 is 3. Okay, so these are kind of frequency distributions that I can create. Basis this frequency distribution, I can create a diagram which is also known as a histogram. Okay, this is something that we may have already seen earlier when we were doing the introduction to pandas. So let me try to draw a histogram if I'm able to draw using the Excel functions. Recommended charts. Let's see if it gives me a histogram. No, it's not giving me histogram. Why? It is not giving me histogram. All charts. Bar box histogram. Yes, I have a histogram, but it is not showing me the correct kind of data. I don't know why. Why it is not showing me the data in the right way. It is only showing me this kind of an output. This is not right. So this is not the right way to represent it. Maybe there is some other way in Excel to do it. But I think you have got my point. So what I'm saying is, if on a straight line I'm going to plot all these numbers, then let's say 5 is here. So the height of 5 is going to be 1. Okay. So this is how I take a histogram. Okay. Then at point number 6, I have how many? 2. So at point number 6, I'm going to have 2. Okay. But there is a problem here. The problem here is that, let's say, I have taken a sample, as of now, I have taken a sample of only 40 houses and the rent of the 40 houses. What happens if my sample is going to be 4,000? Okay. It is quite possible. There are millions of houses in our country, right? So my sample size can go up to 4,000. In which case, you imagine looking at a graph which is something like this with 4,000 lines like this. Okay, so a graph with 4,000 lines like this is going to be very difficult to comprehend. So we need to do something, and that's where we can consider a concept known as class intervals. So what does class interval means is that, let's say I have a rent and I have the frequency. So rather than taking each and every rent or each and every value of rent, what I'm going to say, what is the frequency where the rent is between 5,000 to 10,000? Why 5 to 10? Okay, let me just change the formatting because it is taking this as general. Yeah, 5 to 10. Right? Okay, there is some problem here, so maybe I'll just use the pen. So 5 to no, this will not be a good idea. This will not be a good idea. Let me go back here. Okay, so the class interval is something like this. So let's say in the range of 5 to 10,000 of rent, I have I don't know, 7 houses. Then from 10 to 15, I have I don't know, 6 houses. From 15 to 20, I'm going to have, let's say, 3 houses, and so on and so forth. So this is how I can create a range based kind of a thing. Now my exercise is going to become easy, but then there are some problems, or there are something that I need to remember when I'm creating a class interval. Class interval is a very consolidated way to represent the data, as you can see, because earlier I was representing the data like 5, 6, 7, 8, 9, and 1, 2, and 4, and 5. For each and every 40 sample points, I was about to have a single entry, and then I was about to count the number of houses which were there, which is something like this, making the graph really difficult to understand. If you plot this, you will come to know, right? But then in this case, this has become really consolidated, so I can really group them, and then I can try to find out the value, right? Now when I'm grouping this, there are certain things that you need to remember. As far as possible, please try to keep the intervals tight and the intervals same. So what I mean by that is, if you look at the difference in the first range, it is 5. Same is the difference in the second range, same is the difference in the third range. So please don't create a class interval where the first interval is of 5 value, second interval is of 10 value, and so on. So please don't do that. Class interval should always be, as far as possible, the intervals of those classes should be equal. Okay. Also, the second thing I would like to suggest, and this is also statistically a good thing to do, please try to limit the number of classes between 10 to 20. A frequency table with less than 10 classes may not really yield you some good results, but a frequency table with more than 20 can even be more confusing. So if we try to limit ourselves between something between, let's say, 10 to 20, 10 to 20 is a good number. We can try to limit ourselves, and that should be fine. The third point to remember, 5 to 10 and 10 to 15 should not have any overlapping points. So what I mean by that is, 5 to 10 essentially means where the range is either 5,000 or any number between 5,000 to 10,000 with 10 exclusive. Okay, 10 is not considered in that range. So if there is any house which has exactly 10,000 range, let's say a 1 BHK flat is there and the rent is exactly 10,000. So I'm not going to consider that. I'm not going to count that in this class interval. That comes in the next class interval. So the start is, so what I can say, the starting value is inclusive while the ending value is exclusive. Okay, these are the 3 rules. When you're creating a class intervals, this is how you can try to create the class intervals and then the frequency. So once you take the frequency and then you try to plot the data, then it becomes very easy, because now you will have only 3 to 4 kind of class intervals, and then the data is going to look something like this. Okay, it is going to look something like this, where this value is 5, this value is 10, this value is 15. This is not a real diagram. Okay, this is just an example diagram to show you what is happening here. Okay, so this class interval that I am also talking about, this in the visualization world, this is also known as bins. Okay, so there will be people or books which will also call them bins. They are also known as class intervals. Okay, here the bin size or the size of the class interval is equal to 5. As you can see, the difference between low and high is equal to 5. So these are known as bins, and each and every bin will have a frequency. This frequency is what? This height is actually determined by the y-axis. So I have a y-axis. It's a very bad y-axis. This one. So if I have a y-axis, I have a y-axis. So let me just see if there is a line. Yeah, I can draw a line like this. Okay. So if I have a y-axis, so this is y-axis here is simply going to be divided into numbers, and then these numbers are going to be, let's say, within 5 to 10 there are actually 7. Okay, so if there are 7, then this value represents a 7 over here. Just a hypothetical example, it doesn't. So now gives you a very consolidated kind of an output, and you can clearly say, okay, from the diagram itself I can see most number of houses are within the range of 20 to 25. This is how I can visually summarize my data. Okay, I think we will have to stop here because I don't think we have time. So let me just stop my sharing. If you have any questions, please do let me know. I will be sharing these notes with you. I'll write some more notes and I will be sharing the notepad as well as the Excel. Meanwhile, if you have any